All right. Good afternoon and welcome, everybody. It's my pleasure to introduce our speaker today, Dr. Katira from the Department of Mechanical Engineering at San Diego State University. Parag is really an interdisciplinary engineer or scientist. We still haven't figured out which one. He got his undergraduate in industrial engineering, his PhD in material science, and has done some really interesting work on active material, soft matter, biomolecular motors, and some modeling cancer cell growth. And today he's going to talk about protein interactions with surfaces. So welcome to Parag, and he's also the new Associate Director of the Computational Sciences and Center. So please welcome.
All right. So first of all, thank you, Sachi, and thank you, Jose. I'm going to talk about a topic that I haven't talked about much before, at least not at the CSRC Colloquium. I've been giving this one for probably the last 4 or 5 years. Every 2 years, I end up giving one. But okay. So as Sachi mentioned, right, I've worked in a lot of different topics, and what happens is I work with somebody who's a biologist or an experimentalist. They look at something and they see some interesting stuff, and they don't know exactly what to make of it. And I'm like, oh, I can make a model that explains what's going on. The problem with obviously doing that is that you can make a model for anything for that matter. I mean, it doesn't, if somebody says, oh, we see a trend that goes up and down, I can say I can make a model for that. And then the next person says, we see in the same system, we see a trend going down and up, I can make a model to explain that. So you have to be very careful in believing everything that I say. Right, I'm not going to go into the details of the different things, but I'm going to focus on protein adsorption. And this is something that I've been working on almost since my PhD. This was my first project, in fact, ever. And why is protein adsorption important? So anybody who's working in the biomedical field, right, say that you're building a device that has to interact with blood samples or whatever, and you're trying to look for specific proteins or something. The idea is that your proteins that you're looking for should not stick to everything else, but should go right to the sensor that you want it to. That means your rest of the surfaces should be protein resistant, right? They shouldn't adsorb the protein. You can also think of biomaterial implants. For example, you're going to stick a needle into the body, stick a catheter, stick a stent, whatever it is. You want to avoid protein sticking to that surface, or if you're not going to avoid protein sticking to that surface, you want very specific proteins to go and stick to the surface. Because depending on what proteins are on the surface, the cells around that object are going to react to it. So if it's the wrong proteins or the proteins stick in a funny way, then the cells around it are going to think, oh, this is a foreign body. This is not what I should be seeing. And they'll start attacking it. Once they start attacking it, then you have inflammatory response. You have a lot of adverse effects, right? And also, if you're trying to engineer devices using proteins, again, you want to localize proteins in specific regions. So all of this, the point is protein adsorption, how proteins stick to surfaces is really important. It's a very important question in any bioengineering related topic. One of the most common ways people prevent adsorption or sticking of proteins to surfaces is by taking the surface and coating it with hydrophilic polymers. So polymers that sort of trap water around them. They love water, and they kind of like to trap these water molecules around them. And so you get these polymers to stick on the surface, and there are many different ways you can get them to stay on the surface, either just through physical adsorption, or you can cross-link them. So for example, if you have a gold surface, then you take your hydrophilic polymer, you stick sulfur group to it, which then forms a bond with the gold surface and it will stick covalently. So it'll be really hard to take it off. Or you can actually have certain specific molecules on the surface itself to which your polymers can actually, from where your polymers can start growing and so on. There's a many different strategies. I'm not going to go into the biochemistry because I actually don't know too much about it. We have some really good biochemistry actually. So if they want to chime in at some point. But the idea is you coat the surface with these hydrophilic polymers, and it seems to work quite nicely. Okay, a lot of devices will actually have this PEG, which is polyethylene glycol coating, or even Teflon coating in the simplest way. So Teflon is again very hydrophilic. So it likes to keep water. And what happens in that scenario is when you have these hydrophilic polymers and you have this water, the protein obviously likes to stick to the surface due to multiple interactions. So the protein can stick to the surface because there is some weak electrostatic attraction between the protein and the surface, or there is potentially a hydrophobic interaction or attraction between the protein and the surface. What does a hydrophobic attraction mean? Hydrophobic is basically parts or regions that do not like water. So they don't want to be around water. So you have a region on the surface which doesn't like water. You have a region on the protein that doesn't like water. They're going to go and stick, and they're going to stick really hard, almost as hard as you can get these bonds to be as hard as covalent bonds. Okay, but now if you have coated the surface with hydrophilic polymers, then these polymers actually like to keep the water around. So for the protein to actually directly interact with the surface, it has to displace that water. Displacing that water will take energy, and so you're increasing the energy barrier that you have to overcome for the protein to actually go and interact and stick to the surface. Again, at any point, if you have a question, just go ahead and ask, okay? And people have tried modeling this process where, okay, you have a protein, you have hydrophilic polymers on the surface. Now the protein is trying to go and stick to the surface. How is it going to do? There are quite a few models, mostly surrounding this original work. Started in 1992. They're still publishing on this stuff even today in many different iterations, applying it to different systems and a lot of different things. But what they said was, okay, you have a hydrophilic polymer, right? And it's sticking out from the surface and it's wriggling around. Okay, so as it's wriggling around, it sometimes comes close, it sometimes goes far. And if it's far, then the protein can kind of try and sneak in. And so what they do here is, this is density functional theory-based model where you actually model each individual atom on the polymer chain and how it's sort of moving about. And you create this profile where you sort of map out the space that the polymers are going to occupy, and you have the protein coming in, and now the protein is sort of interacting with the polymers, with the open space, and you see how long does it take for this protein to actually find an opening where it can go in and stick. It's a very complicated model. It had like 12 different parameters, right? Because the interaction between different elements of the protein to different elements of the polymer, interaction between different elements of the polymer and the surface, and all of that stuff, and the energy of bending for different bonds, and yeah. So it has a lot of parameters, but you can explain the data very beautifully. So this is experimental data, black dots, right? Which is the amount of protein that sticks on the surface as a function of the grafting coverage, basically what fraction of my surface is covered by these polymers. Okay, as you can see, it looks beautiful. It looks, and they can actually create these very nice kinks, and yeah, you can fit it. Problem is, you're fitting something with like 11, 12 floating parameters where you don't know the exact value. So sure, you can fit anything, right? I mean, there is this beautiful paper. It's like, give me 4 parameters and I can make an elephant. I can fit an elephant. Give me a 5th parameter. I can make its trunk move up and down. Actually, somebody did that with just 1 parameter recently. So that's a completely different story. But
and that makes sense. That makes sense because your straight line is basically 2 parameters.
Right.
It's almost a straight line. Yeah.
Yeah. And so the biggest issue is fine. They're fitting it, okay, and they're able to show everything. But what they're doing is they're still fitting the 0. So they're saying that that point, at that grafting coverage, you have 0 protein adsorption. And that's again completely not true, because that is actually not your absolute 0. That's just the limit of detection of how many proteins you can see on the surface, depending on what method you're using to measure, to count the number of proteins. And so, yeah, you come up with this fancy equation, and you can explain stuff. And I'm not saying that it's wrong. It was just, it didn't. The reason we went into this whole process was we had a collaborator who was making these surfaces with grafted polymers, and they were like, oh, if I graft a polymer which has 2 arms versus 1 arm, does it make a difference, right? And so we were like, okay, let's think about it. So we wanted to use some mathematical model to predict if it's going to make a difference or not. And we came across this model, and we're like, there's no way we're going to be able to use this. So what do we do? And so we're like, okay, let's think of it, about the problem from a our own science. So he said, okay, you have these hydrophilic polymers. They love to retain water, right? The polymer is sort of fluctuating. And so it has a certain volume, excluded volume, where it traps the water. And that has to do with the radius of gyration of this polymer, which is when the polymer is thermally fluctuating, it can, go around, move around, or whatever. And there is sort of an end-to-end distance between the two, one end tethered to the surface and the free end of the polymer, right? And so we say that sort of a spherical diameter of that radius of gyration of this polymer is a volume that is excluded by the polymer, because the polymer is sort of kind of moving, floating around within that space and trapping the water there, right? So that's excluded volume the protein cannot access, right? And so you have these proteins that are, polymers that are grafted on the surface. These are these black circles with squiggly lines. And the circle is actually the excluded space of volume, right? And so now your protein is trying to find the surface, and it cannot go into this excluded volume. And that's about it, right? So that's just the model. And you say now these polymers are not grafted on perfect even sites. So in the model previously that I showed, the distance between two polymers is exactly fixed, okay? What we're saying is it's randomly distributed, because you're grafting these, but you're not actually putting them right on top, wherever you want them. So it's a random process. And so you have this random arrangement of polymers on the surface. And what that means is that you can end up with holes that are big enough for a protein to sit. All right. And so we calculate how big does that hole have to be. Yeah.
So these water pockets, that's excluded volume. Is that just for the grafting, or because the polymer is some kind of a random block grafted, is that also influenced by the water, or the structure of the polymer is with the random block?
So yeah, so we actually go into the literature and say, look, this is a polyethylene glycol chain with 20 whatever bonds or whatever, right? See, there is a very nice characterization of what the radius of gyration of that polymer is going to be.
Depending on the amount of water around or not?
Well, so there is a lot of water, right? So there is no, it can be as hydrated as it wants it to be. So yeah, there is this
So you say, what is the radius of gyration in a watery?
Right, in a highly saturated, water saturated region, yeah. And so what you do is, okay, you can actually do some simple geometry to say, what if this is the size of my protein, that is the size of the radius of gyration of that molecule. What is the empty space that I need for this protein to stick in? Okay, so if this is the space that I need for the protein to stick in, and there is a certain grafting density, which means that my polymers are grafted at some density, but they're still random, then I can calculate using a simple binomial distribution, what is the probability that within this opening space, there is no additional protein, right? So if I take a protein, I say, okay, now it's going to interact with the surface. What is the likelihood that there is an open spot which has no polymer within that region, right? So the probability of finding a polymer within one single space, like if I divide it up into grids, is 1 over square root of rho of the distance is 1 over square root of rho 0, and then my grafting density gives me the probability of finding that. And then you make a grid basically, where you say, okay, there are these many at the most I can fit in. At each spot, there is probability P of finding one or not finding one, so that I have an average density. And you say, okay, so what is the likelihood that there are none there, right? And so that's your grafting. If you have a grafting ratio, you have the area of interaction that you need open, maximum number of polymers that can be in that area is the grafting density times the area of the polymer. The probability that there are no polymers in this area, it's a binomial distribution. Okay. Now, obviously, I put in a protein. That means another protein can come and sit there too. So there is another probability. So you have, what is the probability that there is no polymer within the area of interaction? And what is the probability that there is no existing protein within the area of interaction? And so you can do the same thing. So probability that there is no polymer, probability that there is no protein, right? And then you say, okay, so what is the probability that a protein interacting with the surface does not encounter any resistance. And you can come up with very simple, very straightforward high school math.
So,
Yeah.
when you generate your probability, it's entirely random, or there is some feature that gives you more probability, like interaction between them or accumulation.
I'll talk to you about that. I'll talk to you. Okay. So, okay. Yeah, I'll come to that. But so you can actually calculate what is the probability that there is no polymer, what is the probability that there is no protein. And so then what is the rate at which your protein will stick to the surface? So you have some collision frequency at which your proteins are hitting the surface. You have a basic sticking probability that if it hits a bare surface, what is the likelihood that it sticks? Again, that is experimentally calculated by others. Then you have a probability that there is no polymer, you have the probability that there is no other protein in that space. Multiply it, you get a simple 1D differential equation, which you can actually solve analytically, and you get an expression. And you can actually find out all of these parameters in experiments. So the no collision rate is a function of the concentration of the protein. The sticking probability, people have actually calculated these for different proteins. It's basically you take a bare surface and you, based on the rate at which your proteins are sticking to the surface, you can actually calculate what is the probability that every encounter leads to a sticking event. You know the radius of gyration of a polymer because you know exactly what you're making your polymer out of. You know the size of a protein that's absorbing. You know all the parameters here. There's no floating parameter.
How good is this? Because you get an analytical solution.
There you go, how good it is.
Well,
Right.
For any problem, complicated, I don't think that you can get an analytical solution that will give you that.
Yeah, you're right. You'll see. But look, it looks pretty, right? It doesn't look that bad. No fit parameters, kind of creating the whole thing. Like, yay.
But even if it wasn't an analytical solution, you would still be able to get like in that case, you were able to solve it, even if it's in turn, like just to reply to the
Right.
It's not even.
No, I know that's
There is more to the story, which will come. Okay. But so this was like no fit parameters, really fairly decent prediction, right? It's not obviously exactly fitting everything, like every curve and cranny, but it fits, it looks pretty. And so I was like, okay, so what this tells you is, oh, yeah, this is again a second set of experimental data from a different group, and again, it kind of fits decently.
Parag, can you go back to the slide? You have 5 different cases. What do they represent and what?
Oh, so the different cases are, so this is EG1OH, basically, so you just have one, sorry? Yeah, one ethylene glycol group. Here you have 2, it's basically the chain length, how many polymer monomers are there in the polymer. And as you increase that, you know, you obviously you're making your polymers bigger, and so that's the difference. And then again, here you have the same polymer, just even further, more bigger ones. And it doesn't depend on the surfaces are coated with different methods, but yeah, so it looks good. We also did something else where people are, instead of coating it just with hydrophilic polymers, what they did was coat the surface with hydrophilic polymers with hydrophobic ends on top. And so what that meant was that you could actually end up with islands where you have hydrophobic groups that sort of cluster together and make a space where there is a secondary adsorption chance of the protein. So the hydrophobic groups together form this island, the protein can stick on the top of that. And so we again modified our equation with a sticking probability to this island where you have at least 6 of these hydrophobic heads stuck together, right? And if that happens, then instead of sticking to the surface, the protein sticks on top of the island. And yeah, you can sort of recreate the curve so where they have this sort of as you increase the density, right? Obviously, as you decrease the density, you have more and more open spots, and you see protein absorption, like the previous case. But now here, as you increase the density, you also have a chance of making these islands onto which proteins can sit, and the likelihood goes up. And that also fits quite nicely. Very surprising. Yeah.
I'm noticing that you're changing proteins, or somebody's changing proteins, right? They're going from smaller proteins to bigger proteins.
Right. So,
But also, you know, changing proteins, you're changing dynamics and surface properties, all sorts of other things. So
Right, and interestingly, none of that matters, right? So yes, these are different proteins, and if they say they're using albumin, we actually go in and take the size of albumin, and that's enough. That's all we need to know about the protein. What is the size of this protein? In fact, the shape changes too. When you say instead of albumin, I'm using fibrinogen or fibronectin or whatever, that's not even a spherical protein, it's a cylindrical protein. And so those geometries matter. But most of these, the examples we picked were like, and preliminary protein adsorption studies are done with spherical proteins like albumin because those are the most abundant ones in your blood, right? Casein, albumin. And so, yeah, these studies were done with these spherical proteins. So it worked out fine. You're right. I mean, if it's a much more complex protein, then things will happen.
So it's just radius of gyration is the only parameter.
Sorry, say that again?
Radius of gyration is the only parameter that you're using for this protein.
Yeah, and the radius of gyration is also actually like experimentally, like for at least polyethylene glycol, you have a nice, beautiful plot that people have made of radius of gyration with the number of monomers.
Sorry, Parag, I think that I have a disconnect that from what Tom is saying now. But you mentioned that you actually got the absorption of the proteins on the surface, which means that implicitly you have the properties of the protein interacting with the surface.
Right. So the implicitly what that comes into the sticking probability.
Yes.
Right. So what is the likelihood that an albumin molecule hits the surface and actually gets stuck?
Which means that if you change the protein, that is a parameter that you need to estimate somehow because that goes into your model.
Right. It doesn't significantly, it's not the most important part in terms of the time scale of the process over which this happens. Right. So your probabilities, those sticking probabilities range somewhere from 10 to the power 8 to 10 to the power 10. Or sorry, 10 to the power minus 8 to 10 to the power minus 10. That's very low. But yeah, even within that range, if I change that, right, my fit doesn't change too much. It's pretty close, it's pretty tight. So within the time scale of the process, when you're looking at protein adsorption over 5 minutes or 30 minutes or whatever, and you have like 10 to the power 13, 14 collisions per second, right? That sticking probability is not that important.
That is important. And then just to clarify, you keep saying feeding, but if I understood correctly, you're not feeding your model to the data.
Right, we're not fitting the models, we're actually just
Making a
putting,
comparison.
yeah, making a comparison. We plug in the values that we know and we draw it, and we plot it. We're not actually fitting it in this case. Still works.
And these values you plug in are for these particular or not? Or just
No, these are values for like the size of the protein, the size of the polymer, all of that is for specifically for this, right? The sticking probabilities are obviously from literature, they're within range, but we don't have to know them exactly. A factor of 10 doesn't make a big difference, one way or the other here. For those sticking probabilities, for these S values. Okay, so quickly to summarize, basically the simple model showed that, you don't need that complicated interaction between proteins and polymers and all these energies or whatever. Okay, great. We were very excited. We published this in a pretty fancy journal. They were pretty excited. All looks great, right? But it actually doesn't. And so the problem here is what we did. So this is actually, the black line is the fit from the analytical model. The red line is actually when we simulate this process where I take a grid, I draw polymers randomly, I draw proteins randomly, and I'm always underestimating. Okay, so we made some mistake somewhere, but it fits. How does it fit? And it fits across many different experimental setups, right? So it's not like, oh, we got one experimental data and our model fits and it's fluke. It actually fits across many experimental systems. So why does it fit? And that was sort of the whole thing that, hey, we made a mistake. It shouldn't have worked, but it works. And so we were trying to figure out why. And what was the mistake in the first place? So the mistake in the first place was that what we did when we were assuming this probability, right, of having no protein inside, we were doing it by assuming what is the maximum number of proteins I can fit within this space. And we did that by assuming that I'm looking at all the empty space that is available, right? And my proteins can occupy that entire empty space. So that's the maximum number of proteins that I can do, which is my sigma 0, which is the maximum protein density without any polymers, reduced by the fractional coverage or by the without any so multiplied by the fractional coverage that is open, or fractional area that is open because of the presence of polymers. That means what I'm assuming is that all my polymers are, if I take all my polymers and I stick them to one side, jam it all up, and then I start fitting my proteins and I fit my proteins exactly perfectly, then our equation works. Okay, but clearly that's not happening because it's supposed to be random, right? So the random adsorption process was actually, the probability calculation was great, but what I'm trying to do is if I take a protein and I drop it on a spot, I calculate the probability that there is no polymer inside, there is no protein inside. Take it back up and drop it another spot. If I take it back up and I drop it on the same spot, now in my analytical solution, I don't have any memory. I don't have any memory that, oh, there was a protein here. So I drop it, I say, oh, there was a protein, I drop it on the same spot and now there is no protein or nothing blocking it. And so now I can stick, right? Because it's a sort of a sequential process. And so that's what helped me overestimate some of these curves. But the fact that it worked was still funny because yes, we were making a mistake, we were overestimating it, but it still works. And so what's going on, right? That means that this assumption that we made, that your surface is fully packed, was not that awful. Well, how is that possible? And so we looked at how they make these surfaces, and they make these surfaces, when they make these surfaces by, say, depositing these polymer chains onto a metal surface or whatever, they don't sit randomly. They actually form clustered islands. Okay, so they actually, the polymers themselves end up clustering together, especially in a few of the methods where you have this formation of self-assembled monolayers. When you have these self-assembled monolayers, they sort of start clumping together. And so if you look at the distribution of the polymers on the surface, you have them sort of clumping together and forming islands. Okay? And even proteins, when they sit on the surface, they don't just sit and stay steady. They'll sort of nudge each other around, and there is another one that's trying to come in. They'll sort of nudge each other around and maybe create spots and spaces. So they can actually tightly fit. Right? So what we did was, like, we took our random model, but the simulated one now, which was the right one, and we incorporated these aspects where you can either have your polymer chains that are growing using a nucleation and growth process where they are clumping together, right? So you have a polymer, another polymer is more likely to sit next to it. Another polymer is more likely to sit next to it. Another polymer is more likely to sit next to it. Obviously, if you have a bunch of polymers and there is just one open space, then it's hard for it to sit, and then that sort of increases the barrier. But putting that sort of this tight fitting between the polymers and also doing the same thing for the proteins, you can have either the polymers are tightly fit, but the proteins are random. Either the polymers are random and the proteins are tightly fit, or you can have both, and then you can have obviously random, right? And when you do that, then for these surfaces which actually have, which are made with self-assembled monolayers, where you see these islands, now they start fitting again, right? So where you have these polymers that are actually sitting in with nucleation and growth, so that means they are actually compact. Now you can recreate these curves very nicely with the same parameters that we assumed for the radius of gyration and the protein size. The interactions are still the exact same. It's just that it's no longer a random distribution. You have them packed in, and now it makes sense again. And in this one, where the polymer is actually not, it's not grown by self-assembled monolayer process, but it's physically absorbed. In that case, the random polymer one fits nicely, but the protein actually nudge each other and sort of tightly fit together. And that's the one that fits the best in that case. And so what I'm trying to say is that the initial assumption that proteins or hydrophilic polymers prevent protein adsorption by trapping water within the radius of gyration or within that specific excluded volume still holds, but what dictates the adsorption of proteins is the underlying packing of these polymers on the surface and how the proteins then interact with each other once they're on the surface. Can they move them around? Okay. So, moral of the story, again, as I said, don't trust everything they said. We got lucky with the other one. It wasn't a completely crappy model. It was a good model. It worked, it fit. There was a mistaken assumption that we made because we had to find that upper bound to calculate the probabilities, and we found that upper bound using this approximation where you said all the open available area is available actually for the protein to set. And that's not entirely true. But then we figured it out that luckily it worked out for us because how these surfaces are formed, you automatically have this packing of either polymers or proteins together.
So I have one curiosity, what happened then with the group that was working since the 90s with the density?
They are still working on their stuff. Obviously, they still use the same kind of model to do a lot of other things like, oh, now I've had two surfaces coated with polymers, what is the energy? So they're still using the same things, maybe made a little bit. One of the biggest changes they did, obviously, after our paper was published, was they stopped taking the distance between the polymers constant. They started making that random. But yeah, they still, I mean, they're DFT people, and they do DFT. So.
Yeah, but there is also like, you probably heard that there's no reason to discard a theory because it's beautiful, but it's wrong. So there is no reason to discard it.
Like what I understand from Parag is that you have a lot of information that you can use up front to the point that you don't need to treat the data.
Right.
So if you start your DFT from there, after you understand all these, it might actually give you an advantage because you can focus on details that you cannot.
Right.
All
I think what they ended up doing was they ended up sort of changing the question altogether. It was no longer about protein adsorption to surfaces, but sort of interaction energies between surfaces and something like that. Now you can sort of taking proteins, now you go to big cells, and now it's a completely different problem. So they say, okay, now can we use interaction between these polymer coated surfaces on a giant cell? And that's much more complicated than just doing proteins. So now, Sorry, I'll let
in the model, you don't explicitly address the energetics, right? The energetics of the polymer to the gyration or can you explain how you can get away without?
So the energetics actually comes, so the energetics of the protein polymer interaction is that the energy barrier is so high because of the trapped water that the protein really can't displace that trapped water from around the polymer. And that's why it acts as a perfect steric barrier. It's like, look, I have this polymer which has all this water molecules surrounding it.
Energetics of the protein interaction. There's the energetics of within the chain for its gyration. There's a lot of things that are determined by the energetics of it in the medium,
Sure,
right? So
we don't need that for this, right? So energy, when you're saying yes, there are energetics involved. My point is that for the protein to pass through this polymeric barrier, if the barrier height is say 30 kT, that height is so much that it's not going to necessarily jump over that within the time frame. It's very unlikely for it to jump over this high energy barrier. 30 kT is not much, but yeah, it's still quite high, right? I mean, the probability that you can overcome that is e raised to minus 30. And yeah, and so you multiply that by the frequency with which it's trying to do that, which is 10 to the power 10 or 12, somewhere around that. And based on the size of the protein, obviously that changes. But yeah, it's still 10 to the power 10 multiplied by e to the power minus 30. It's 0.00005 or 0.006 or something like that, like 10 to the power minus 3 or 4 or 5. It's pretty low. That's the point. And so, and the interaction energies between the surface and the protein, they come into effect in that sticking probability parameter.
That's the word confusion actually. Does polymer dynamically do they change? Or it,
No, so polymer once
don't
they're
change
on the
dynamic.
surface, wherever they sit, then they don't.
this is fixed.
Yeah.
Only protein try to.
The way they're forming those
But
bonds, yeah.
Isn't that possible that?
That is possible, yes, there are-
And if that is possible, then what you are saying before is not correct. You are saying One time it cannot there, next time it can, but that's possible, right?
That is possible, yeah, you're right. I mean, that is also possible. But I don't think that the polymers are themselves diffusing too much on the surface. I'm not saying it's impossible. I think they can.
I was just connecting to, let's say, the lipid membrane.
Right.
And the receptors of the cell is the protein, if you think of it,
Right.
then they can move around
Yeah.
on that one. So that's.
Yeah, absolutely. Yeah, we didn't do that. Okay. So this one actually has a bit more of the energetics, if you're really interested in that. This is a slightly different problem, again related to proteins sticking on surfaces. This is more recent observation. So what happens is when you take a surface, you coat it with proteins, or you put in a solution which has proteins, you let them stick, and you measure how much proteins are sticking. That's what this looks like. Okay, your protein coverage is going up. And then you wait for a while, the protein coverage reaches a point, and then you flow the solution out. So now there is no more solution in the, there's no more protein in the solution. Right? The protein on the surface starts popping off, and that starts going down too. Okay. And so now your coverage kind of starts decreasing. And what people do is they take this rate at which the protein is leaving the surface and fit an exponential curve, and you get the desorption rate of protein. So if protein comes and sits, what is the rate at which it falls off? You get a nice exponential fit to that, and you get the rate of protein desorption. Awesome. So for until at least like last 8 or 9 years ago, right? Everybody assumed that protein desorption kinetics follows this exponential. Okay, you have one rate at which proteins fall off the surface. Then they started looking at individual proteins using cool microscopy techniques where you're looking at just individual proteins. And so you see the protein come and sit on the surface, and you're tracking it now. What is it doing? And then you see it fall off. And you can plot actual time that this protein spent on the surface. So instead of this bulk measurement fit, you get individual residence times of how long the protein sits on the surface. And it looks something like that. And this is a log normal scale. So that's not an exponential. If it was an exponential, then it would be a straight line, right? It's not a straight line. So clearly it's not exponential. Okay, great. How do you explain it? You explain it with sum of multiple exponentials. You say, oh, if it's not one exponential, I can add one exponential, second exponential, third exponential, fourth exponential. Okay. That's what people do. And you can do that. So that's your probability or residence time distribution, which is the sum of multiple exponentials. And the way you explain that is that, oh, I'm not looking at a single protein sitting on the surface. My proteins come in different flavors. So I can have a monomer, I can have a dimer, I can have a trimer, or I can have a tetramer. Right? And if I have 4 different populations, then I should have 4 different sticking residence times. And that's what I'm seeing. So I can fit 4. Or you can say that they're not all sticking to the same site. Every site is different because my surface is heterogeneous. So I can sit sometimes in a very sticky place. I can sit sometimes in a less sticky place. And so I can defend my multiple exponentials. The question is, how many exponentials do you do that? Right? You can do infinite number of exponentials. Hey, but then you do a math. So the common way to do it is you do a maximum entropy fit, where you say, okay, what is the minimum number of these exponentials I need to explain my data? And sometimes comes out to be 3 to 4, works pretty decent. Okay. Yeah. We didn't like the explanation. I'm like, but yeah, but you're saying it's 3, you're saying it's 4, you can say it's 5, you can say it's 10, right? How do you know? And even if you do like 3 or 4, you still say, if you say 4 exponentials, that's still 8 parameters, right? Why? You don't like it. Want to do something else? And so then what we said was, okay, let's look at this, right? So instead of plotting on the log normal scale, you plot it on the log, you get this really strict linear regime, and then you get this, which is the last exponential one. And I was like, oh, look, this regime is actually power law. So the residence time distribution will be power law. Everything was power law at that point. I mean, this was 2017, and it was a big deal, like, oh, BC power law, you know? And so I was like, that's power law. Okay, great. How do you explain? I mean, it doesn't matter if I say multiple exponentials or power law, because power laws can be approximated with multiple exponentials. So I don't think one or the other is the important part. The important part is the mechanism. What gives rise to this behavior? And with the multiple exponentials, they had an explanation. If we want to say power law, then we have to come up with an explanation of why is it a power. And so I said, okay, what are the other processes that give you power law? One of them is the gambler's ruin problem. You know, I say I start off with $1 and I can bet $1. How long will I be playing the game? And if I have a certain probability that I'll win, I have a certain probability that I'll lose. So I could lose in my first chance, or I can win. So I go to $2, then I still bet 1 again. I can go to either 1 or 3, right? And so the time that I play, if it's an infinite, I can get as much money as I want to have, infinite amount of money to win, then that will actually look like a power. So like, oh, well, maybe this is a 1D random walk process where the protein does not actually come and sit on the surface and you form a bond and you're done. It actually comes and sits on the surface and then says, oh, maybe I can stick better. Maybe I can stick better. And you have this equal likelihood of going in one. You don't have to have equal. You have likelihood of going to the next configuration or to the previous configuration. And so then what do you get? And we're saying that you cannot have infinite states because at some point the protein, it's hard for it to unfold more. And so if you do that, look, it fits. Right? So the parameters here are the speed probability is the likelihood that you jump back to a previous state. So 1 minus p is the probability that you jump forward. The tau is the time where you sit in one piece. It's like, okay, I'm going to wait here now, and then I'm going to go this way or that way. And again, tau is not, it's the average waiting time, right? And n is the number of jumps you can make. And so for this protein, this is fibrinogen adsorption to silica. You get this probability of going to the backwards stage is 0.367. The waiting time is 6 seconds. The number of stages you can unfold to is 4. But like, great, 4 is awesome because fibrinogen actually has 4 different monomeric structures or different globular structures that come together to form this fibrinogen protein. 4 was great. Yeah.
Why would the probability of changing the combination of each of those ways be the same?
It doesn't have to be. It doesn't have to be. So I'm assuming there's a P in and a P out, but as long as there is a common average P in and a P out and not very, and they don't vary too much, I'll still get the similar output. I'll show that. The potential explanation is that for every conformation to change, you're probably breaking a similar number of hydrogen bonds or whatever, and you're unfolding. So the energies can be different, but not too different. It's not like, oh, I have these two and I'm not breaking an egg. I'm just one by one, little by little by little, right? So yeah, it seems feasible that the energy levels will be more or less the same. The barriers to overcome that. But it doesn't have to be exactly the same every time. I can have fluctuations in those, right?
So
yeah.
This one is your results of like your simulation.
Yes.
Like
No, so the red is actually experimental.
No, I got it.
And blue
So
is
the blue one.
Yeah.
Why is it so nice?
What do you mean? Why is it so nice?
Smooth. You don't have a little bit wiggly. That's what I was expecting. It's
So this
nice
is
or
no. So
like
this is a million events,
Okay.
right? Where you look at how long each one stays, and yeah, if I do 10 events or 100 events, then yeah, I'll have, better distribution. But yeah, a million events kind of smooths out quite nicely.
Can you explain the mechanics then? So does that mean on your polymer you have specific sites that are better located for it to absorb? Is that why it's changing positions?
Not even necessarily better size, but let's say you have a protein that sits, right, and it forms one bond, and now it's wriggling around. It's not a rigid structure, and so it forms this one. That one comes to the surface and it interacts. It's like, oh, okay, I can form. And then the next one. Now, if I want to rip off, I can't rip the entire structure off. I have to kind of, it's like a zippering problem. Basically, I form one bond at a time because the other bond didn't have the space to access the site, but this one has formed, now this one can access, and then the next one can access as it sort of unfolds or whatever, right? And so you can have this 1D process. You cannot jump over. Maybe you can, but the energy barriers are quite high to do that.
But now that's the energy of unfolding the protein.
Yeah, it's not completely unfolding, but the small conformational changes in the protein, yes, right, as it comes to the surface. And something like this, right, like where you have these structures, so the first one sat, now the second one can sit, the third one can say, oh, look, I can sit now, the fourth one. If I want to take it off, I have to again kind of, I can't directly take those two off and it's done. So this is more likely to come off, and then the next one and so on. So I have to kind of do this in a sequence. Like the zippering process. Again, we don't know if this is 100% true, but this is one potential explanation, which works with three fit parameters, right? Obviously, it has fit parameters, but 3 fit parameters compared to 6 or 8. So we're kind of excited about it. And you can also say what these parameters actually mean. So when I say I have a probability of going back or going forward, right, and I have a waiting time, and I can actually say what is the rate at which it goes to the back state? What is the rate at which it goes to the forward state? What is the difference in the height of the energy barriers? Right. So this is going forward, this is going back. What is the height, difference in the height? And that's half a kT. And what is the height of this barrier itself, which is dependent on the tau? How long are you going to wait? That decides the height of the barrier, and that's 25 kT. And all of these are reasonable for protein absorption and what we know about it.
Those 3 parameters are fitted now.
Yeah, so the probability of going back or going forward, 1 minus that, the time which it waits, and how many of these confirmations it can access.
One question, Parag. Can you go to the prior?
This one?
No, the one that you had before. So on some of these systems that you start having these emerging properties and power laws, the part on the right, since residence times that are much longer, are very sensitive on how long you actually do
Yeah.
experiments, and
Right.
that means that depends on how long you end up measuring it, that can be shifting. And in your case, are you able to either predict how sensitive you're going to be to that, or you can actually say, doesn't matter really how long you measure from here on, you're always going to be seeing this shorter?
So no, so these are corrected times based on there are multiple ways you can actually correct for these residence times at the tail, right? Because you're not observing many events of those long ones. There are ways they correct for it. We were never able to exactly fit this space, but
So then you're saying that in asymptotic time measurement, that will change. That's it.
this one for my fit.
For the experiments.
No, yeah, it doesn't change. If I change, yeah. So if I look, so we went through this. We said, okay, if I instead of looking for 2 minutes, I look for 3 minutes or 4 minutes.
Yes.
That shouldn't change, yes. And so that's where the correction thing, you say, okay, which correction factor actually works best. It did matter if we did this. Okay, so this is for computational guys. There are 2 ways you can count. Like you look at a protein, you come, it sits on the surface and it goes off, and you're recording this video. And so you look at frames now. Okay, frame 1, protein came. Frame 2 is there, went off. Oh, came back. So that means I was blinking. So you have to make sure that you connect those dots. If it's right exactly in the same spot, then it actually never went off. It was just blinking on and off, because these are fluorescent proteins. So they don't stay bright all the time, right? And so you correct for those things, you connect those trajectories. And then now it went off and it hasn't come back for a long time, a certain amount of time. Then you say, okay, that was the time it was sitting on the surface. And then you can automate this where you're doing particle tracking. You're connecting. Automation does not work. We've tried it with softwares from a bunch of different labs. The best way to do it is to sit and count by hand. So yeah, if anybody's interested in that problem, they can look at how to really automate it and make sure that it's working, right? Okay. So obviously, but multiple exponential also fits, right? You have the best one was with n equal to 4 again, but you have 8 parameters that you fit. So the thing is that multiple exponentials sort of meant that they're looking at presence of different populations, or at least 4 different populations. The point here is that we did not actually see 4 different populations. So we picked out these points and we plotted their intensity, The idea is that if it's monomer versus dimer versus tetramer or trimer versus tetramer, then their intensities are going to be different as well, because the number of fluorophores you have to attach to each protein is the same. So you have 2 of them, that means twice the intensity, 3 of them, 3 times the intensity. So we look at the histogram of these intensities, and you can break out saying like, oh, this population is monomers, this population is dimers, this is trimers, this is tetramers. And you look at the residence time, and there's not a significant difference. Even if you take out like this entire short timescale population, the rest of them still look exactly the same. So we did not see the evidence for 4 different populations. Well, that's one other reason why we like our model. In the event of time, I'm not going to go too much over this, but this was sort of looking at what do the 3 parameters mean in terms of if I change n, what is really changing, right? If I change it, what am I really changing? If I change my p, then what am I changing, and how it changes the shape? And if I change my tau, how that changes the shape? And then this one is how good our fit was to some extent. Because again, the way we are fitting this is it's a simulation, right? So we simulate with one set of parameters. We look at the fit. We say, is it good or not? We calculate the modified R square. And then we choose the next set of parameters, and we do this Monte Carlo search process to find the best fit. It's a painful process, especially when in a simulation you're doing million proteins. Simulations take a while. Like to find that space, it's painful. But we were able to do it, and we obviously the question was, how do you know if it's n equal to 4 or n equal to 6? Does it make a difference? And it does make a difference. If I go to n equal to 3, you can clearly see the fit changes quite significantly compared to n equal to 5. Obviously, n can be only integers. Again, with the waiting times, the fit changes not too badly, but n tau equal to 6 works best. With the choice of your p, the probability of jumping back or forward, again, it changes, but not too much. That 0.367 that we took was somewhere in between the range. So, and then this one was the question that was asked, which had to do with, do these probabilities have to be the exact same between stages? And the answer is, look, I can make I can randomly choose these probabilities of, if you're in state 1, then the probability of going forward or backward is this value plus or minus something, right? So it's around, so the mean is the same across these stages, but they're a little bit higher or a little bit lower between stages. And the fits look not too bad, they're similar to their nature. So it doesn't affect it too much. In fact, it might help you fit the data better, this heterogeneity between these individual stages. But obviously, we don't want to go into that process, because if I say there are 4 stages, then I add all these different parameters that I'm looking for. So we just let's assume there is one average probability of going forward and one average probability of going backward. And so in conclusion, what we're saying is that the protein absorption process by itself, sort of the zippering process where the protein sits on the surface and then, sort of zippers in to a more well-bound state versus zippers up. Now, what does this mean for other things? Because we were assuming exponential times, that means we were assuming there was one fixed rate for the proteins to get off, right? But there isn't. It's actually a power law distribution. And so that means all the kinetics that we calculate in our like pharmacodynamics, pharmacokinetics, or whatever, or protein-protein interactions will not stay true because you don't have that one dissociation rate. It's time dependent, in fact. So what does that mean? That's something we're contemplating. But with that, I will end this. Most of the work that I talked about was done by master student Jeffrey and undergrad student Peter. And actually, yeah, Peter Solomon obviously contributed to the zippering model. Again, takeaway, you can model processes in many different ways. You have to be very careful. And it's all about the insights that you get from it, and does it make sense, or, yeah, I mean, you can explain the same thing in many different ways, right? Is it right? Is it perfect? Does it make sense? It all depends on what question you're asking, what you're trying to get out of the model. You have to be careful about those things. Yeah.
So the publication, were you able to get it out?
Yeah, that one came out in last year in Langford. I can send you the paper.
Just the curiosity, you have two approaches, like you get P, tau, and
N.
N, right?
Yeah.
And that N is 4, and your exponential also, you just fit it about 4.
Yeah.
Is there any connection or number of parameter connection? Because usually, why exponential, single exponential logarithmic transform for that,
Mhm.
but if you have a biphasic kind of things,
Right.
that means there are two mechanisms that is governing, that's why you need number of
Right.
exponential term. Is it because of like a first decay is due to maybe that tau timing?
So that's
or
the-
second decay might come due to going back or something like, is there a way think that?
No,
that-
so
that might be described?
The way people who fit multiple exponentials, they explain the 4 by the presence of monomers, dimers, trimers, tetramers. The way we explain our 4 is that the structure of fibrinogen has 4 distinct subunits. And so maybe each subunit is sort of unfolding and sitting. Beyond that, I don't know if there is another real connection. And again, it's a maximum entropy fit, like n equal to 4. You can go with n equal to 5 and it'll still fit. It'll fit better, right? It's just, yeah, you don't need it to really fit it well. There is a penalty on how many parameters you add to that fit problem. So, but yeah.
Any questions out there?
Oh, yeah. Any questions? Let's see. Anybody has raised their hands? I don't know. No, I don't see any questions. Yeah.
So in an energetic interpretation, there's some finite probability of having enough energy to break more than one bond, like tearing a zipper apart.
Yeah.
Have you considered that, or have you like calculated it based on your energetic interpretation? I'm just wondering if, you know.
Yeah, I mean,
It would be better if you included that consideration.
yeah, so it's like now instead of breaking one bond at a time, let's say you also have a certain smaller likelihood of breaking 2 bonds at a time, and an even smaller likelihood of breaking 3 bonds at a time, and an even smaller likelihood of breaking all the bonds in one go, right? But that changes pretty quickly because each of these bonds are about 25 kT from the looks of it, but the difference is half a kT. So yeah, I don't know, it is possible.
It's just thermal fluctuation, right?
I think,
In terms of imparting enough energy to break it down.
right, but I think it has to do with conformation, where it's like I can't access that bond until I do this, because now my protein has unfolded a little bit more, so now that guy has access. Otherwise, before that, it didn't even have access to the site.
These are really two-dimensional bonds.
Yeah.
You got it like a one-dimensional zipper, but there's nothing to say that two-dimensional.
Right? No, it is, yeah. So it's like walking on a 2-dimensional surface, right? So. This one here, right? It's sort of like a 3D where, yeah, I mean, it's a 3-dimensional space and you're jumping from one well to the other. And it's like, I can only access that well if I go to this well and that well. But if I want to go over, there's a huge, really hard barrier. Again, how realistic it is, I don't know, but it's not unrealistic either.
Well, I'm just saying, you know, in your mind, scatter the bonding sites in 2 dimensions. Because something happens to the third one.
Yeah, it would be really nice to actually. It would be really nice to actually plot the energy surface, right, of these bonds and how they go. But yeah, I think if you have a way of doing that, I'm happy to. It's complicating the problem more than what we were interested in. It's like, okay, why do we get these distributions? And now we have a secondary explanation or a different explanation, which we like more because obviously we came up with it. But it doesn't have to be absolutely right. It's fewer fit parameters. It seems to make sense. Now, if there is somebody who can look at individual states of proteins as they're binding to the surface and see this folding, unfolding process and map out the energies, then yeah, right, there is more to that. We don't have the skills to do that. I don't have the skills to even look at the proteins and like this stuff. So I just like to do the math.
one more curiosity. Your surface is flat, right?
Yes.
Have you thought of making curved surface? That would be very,
There's no
lot
flat
of
surface.
applications.
There's no flat surface, that's just a.
Right, but the question is, what
No,
is the
it's not
roughness?
mathematics,
What
because
level is
that's
the
a
roughness?
huge
Because your protein is 5
implications of
nanometer.
Aerosol infection.
Mhm.
Yeah. And your receptor protection, it sounds so applicable. I was just curious how difficult
Right.
it is. It's not, I don't know,
I
just
don't-
curious.
I don't think it's difficult. I just don't know is it really important? Is it relevant? Does it matter to the overall dynamics of the process or the kinetics that you get, like how long it takes? I don't know. Maybe a simple exponential is enough, right? Because you have this power law truncated to the
Your
exponential.
curvature might matter.
I mean, yeah, it might
so
matter to
you
the
think of
process.
It's very tiny and growing up, maybe it's a flat,
Right.
but your curvature plays a role in,
Yeah.
in actual.
Sure. So when I'm
Yeah.
thinking about two proteins where I have two 5 nanometer spheres, now they're trying to stick. It will matter even more probably. Maybe it matters less because now you just have this one attachment point and you can't really, so yeah. If n is equal to 1, then you end up with an exponential.
All right. We can continue the discussion. The author is at our disposal for the next hour.
Actually, I'm not, but yeah, I have to go pick up my kids. Sorry.
He's bailing out. So, all right. Thank you, everybody, for coming. Have a good weekend.